Hi, we are analyzing problems using the principle of impulse and momentum. So here we have a girl, this is a girl, it's in green, and a boy. They are together in a sled, so they start here at A, and they go down the slope, right, with no friction. So friction between the toboggan and the slope is neglected. Whenever they hit the bottom of the slope, let's call this point B, the boy is pushed back, and they ask us to find the velocity of the toboggan after it's pushed backwards. So the first step that we have to do in the solution, so first thing we have to do is find the velocity when they arrive to B. And when they arrive to B, they are still all together, right? Find velocity when arrive to B. So to do that, we notice that since we don't have frictions and we have a height and they go down and they start at rest at A, so we could use the principle of work and energy. And we do not have any non-conservative forces, so we have conservation of energies. To find that, I will use conservation of energy. So let me name this position 0 and this position 1, and we can write that the T1 plus V1 is equals to T0 plus V0. Being 0, that position at A, right? So if we put our datum up here, so we will have that we have rest, so it means 0 kinetic energy, and since we put our datum right there, we have 0 potential energy. So we have only a position 1, which is this one at B. We have a kinetic energy, which is 1/2 total mass, velocity of the sled at position 1 square, plus the potential energy. Since I went down, I lost potential energy, so that will be negative. Let me change that positive to a negative. Negative mass, total mass again, gravity, that's equals to 0. Those total mass are the same, so we can say that the velocity when they arrive at position 1 will be equals to 2 gravity high at that position. So we here have that velocity 1 is equals to 9.81, the distance, which is 3, and then we have that the velocity 1 is equals to, I have this value calculated, 7.67 meters over second. This will be our step 1. Step 2. Step 2 is now analyzing what happened when the boy is pushed back of the sled. So this I will use the principle of impulse and momentum. And what I will do, in order not to consider the internal impulse, because when the boy is pushed back, he receives an impulse, but he produces exactly the same impulse to the girl and the sled. So I'm going to draw those two together still, right? And then the internal impulse right here, we don't notice between the two. And since we don't have any friction, we don't have any impulse between the sled and the ground or the snow in this case. So we know that the impulse and momentum, we have that the impulse, right, the summation of all the impulse will be equals to the summation of all the linear momentums in position 2 minus the linear momentum of all the components in position 1. We just found the velocities in position 1, right? And we have to find the velocities in position 2. Since we don't have any impulse, because the only impulse is intern, so we have that this is equals to 0. What do we have in position 2? We have that in position 2, the boy already fell, right? It's pushed back, so the mass of the toboggan plus the mass of the girl will have the one velocity, let's call it velocity 2 of the toboggan, plus the boy will have a different velocity, and the initial velocity all together have the same velocity. So that will be mass of the toboggan plus mass of the girl plus mass of the boy multiplied by the velocity of the initial, which is this one that we calculated here. I'm going to make that, since this is a negative sign, this is equals to 0, right? So this is actually, those two quantities are equal. So here we know this quantity. Let's substitute all the masses. So we have the toboggan plus the girl will be 50, velocity 2 of the toboggan, plus the boy is 45, velocity 2 of the boy, equals to the complete mass of it will be 95 times this velocity that I just found. So at the end we have this equation right here, but we have two unknowns, and the unknown is the toboggan and the boy. But we know the relative velocity from the boy respect to the toboggan. So we can say that my other equation will become that the velocity of the boy will be equals to velocity of the toboggan plus the relative velocity of the boy respect to the toboggan. We know that the toboggan is going in one direction and the relative velocity is going in the opposite direction. So it depends what we name positive. If we want to calculate the velocity of the toboggan, we can say that this is positive, for example, and then the relative velocity of the boy will be in the other direction. So we can write here that the velocity of the boy is equals to, this is absolute velocity, because here in the equation of linear momentum or conservation of linear momentum, this is, let me write that down right here, conservation of linear momentum, all these velocities have to be absolute. So we have the velocity of the absolute velocity of the toboggan, and since they are in different direction, I will put minus is given is minus 2 meters over second. And this will be my second equation. So I have equation right here, 1, and I have equation 2. And this is obviously for position 2. So I could substitute that into here and solve the system simultaneously. So solving, I'm going to write the result, solving 1 and 2, which is a very easy system to solve, right? Where I plug this into here, and then I get only that velocity of the toboggan, and the velocity of the toboggan is equals to 8.62 meters over second, and the velocity of the boy is equals to 6.61 meters over second. Please note that both are positive. What it means positive in this case. So both are in this direction. So even though that the boy is falling down, he carries so much velocity that he falls down, so it's a little bit less than the toboggan because they subtract, but still in that direction. So the boy still moves forward in the same direction as the toboggan.